Hi, my name is Neil Tamarani, and this is my Lab 3 surrounding the magnetic field of a bar magnet. So for our introduction, some of the goals were to investigate the distance dependence of a magnetic field of a small bar magnet, to simulate the magnetic field of a bar magnet using VPython, and then to compare the measured and simulated magnetic fields. So for our findings, the magnitude of the net magnetic field increases, the distance decreases, the magnetic dipole moment is roughly 1.4875, the measured off-axis magnetic field is 7.45 e to the negative fifth teslas, the simulated off-axis magnetic field is 2.947 e to the negative fifth teslas. When it comes to our key concepts, some of them included the Biot-Savart law, which relates the magnetic field produced by an object at an observation point in teslas to the current I running through the object and the distance between the source of the field and the observation point. Here's some other formulas that were used, and one of the important ones was the magnetic dipole moment, which was equal to the current times the loop area. And to note, the direction of the on-axis magnetic field is the same direction as the magnetic dipole moment in the conventional current I. For our other key formulas, we use the fact that the magnitude of the magnetic field of a magnetic dipole on the perpendicular axis, which was opposite to the magnetic dipole moment, the magnitude of the magnetic field due to a bar magnet, and a general formula for the magnetic fields of a magnetic dipole. For our visual model, the system was our observation point, which is to the right, which was the magnetometer, and then our surroundings were the bar magnet, which produced the magnetic field. And then as a part of it, for the magnetic field of a bar magnet, we treated the bar magnet as a magnetic dipole. For our procedure, our materials are listed. Something we had to do is compensate for the magnetic north by orienting our phone properly. We had to find the magnetometer chip. And then for measuring the on-axis magnetic field, we measured the distance between the magnet and the magnetometer, where the magnetometer is on axis to the dipole axis of the magnet. And we did that for a few different measurements. And then we measured the off-axis magnetic field. So we measured the on-axis distance between the magnet and the magnetometer, such that the magnitude of the net magnetic field is 100 teslas. Here are some of the visual modules that we used. And then here's the data analysis and results given the Excel file and the graph. So as a part of it, we derive this equation where the slope of the regression line equals n, and the y-intercept equals the natural log of k. So we solve for k using Euler's constant and the exponential function, and then using the constants derived from the regression line, we found the equation k times r to the n equals mu sub 0 over 4 pi times 2 mu over r to the third. To note, the corrected magnetic field in the y direction was calculated by subtracting the Earth's magnetic field from the measured y component of the magnetic field at the off-axis point. Some of our observations were that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. So for our computational model, we have our constants in our magnetic field function that we established. And then here's where we dealt with our arrow scaling and drawing arrows for the magnetic field. And then in the final part, we created the off-axis magnetic field and magnetic field arrow. And here's what the VPython result was. For the discussion portion, as the distance between the magnetometer or observation point and the magnet decreases, the magnitude of the magnetic field increases. At 20 teslas, the distance was 2.16 e to the negative 1 meters. And at 70 teslas, the distance was 1.43 e to the negative 1 meters. Our magnetic dipole moment was 1.4875. The experimental magnitude of the magnetic field off-axis was 7.453 e to the negative fifth teslas for the magnitude. And then for the simulated magnetic field off-axis magnitude, it was 2.95 e to the negative fifth, which means that there's an 86% difference in the net magnetic field magnitude between the experimental and the simulated versions. And some of the possible sources of error would be placement of the measurement tools regarding the magnetic field and any other interference, as well as measurement errors. So if we hadn't compensated for the magnetic north, our x and y components would have been different, but our z component wouldn't have been affected, and that would have been because we did not account for the magnetic north. And then if we were to stick two identical magnets together, end to end, and run the experiment again, the difference would be that the magnitude of the magnetic field would increase, and it'd be close to double given the rules of superposition due to the combined magnetic fields of the two magnets.